welcome everyone. This is the Flower Monthly session for November. It's November 6th, and we have, I think, a pretty exciting set of updates. First, coming from the Flower team, I will go through them fairly fast. There are some interesting updates probably you are curious to hear about, and then we'll jump into two excellent talks we're going to have. One is titled, Where is the testbed for federated learning research? It's going to be presented by Amandio and Janes, who both were in Flower Summit last year. This year, sorry. I wasn't fully aware of that, but they reminded me. So it's great to welcome them back to a Flower event. And then after this, we're going to have another talk titled Flower Serverless, a serverless and asynchronous federated learning recipe for medical imaging, which is going to be presented by, I forgot the name, sorry. ZZC. And this is something I'm quite excited to hear about, how you made it work in asynchronous with Flower. So without further ado, let's start with an update. So the main update is that we have announced the Flower AI Summit 2025 is going to be in London once more, in the same venue as last year. I think it was an excellent experience, the one we had earlier in March this year. So it's going to be again in March, but this time on a Wednesday and Thursday, which makes it even more attractive. So if you're coming from far, you can spend the rest of the weekend in London, which is always super nice. Registrations are already open, and you are welcome also to submit a talk or a poster if you have something you would like to share with the Flower team and the broad Flower community that is going to be present there. Just like Flower Summit 2024, there are going to be a research day and an industry day, and each of them is going to have their own overall theme, but everyone is invited to both days, and you will find the agenda for it in a few weeks' time. If you want to, well, you probably have seen posts about this on LinkedIn, but if you want to find the specific page about the AI Summit 2025, the easiest is to go to flower.ai, and then in events, you can see the link to Flower AI Summit 2025. If you have any questions about poster registration or submitting a talk, feel free to reach out to us on Slack or ask any question here during this session. The second piece of news I wanted to share is that we have launched the Flower Tune LLM leaderboard, which was announced in the Flower AI Summit 2024. The idea here is that we present 4 different leaderboards, each targeting a particular use case. One is general NLP, finance, medical, and coding. And the idea is, given a pre-trained LLM, can we federate the fine-tuning of these models in one of these particular use cases? So similarly to other activities we have put together, like the Summit of Reproducibility last year, the process to participate here is fairly simple. It is comprised of 4 stages that are some highlighted in this diagram. You just need to choose the type of task you're interested in, for example, medical. Then you can start your code from a given template that is a model that works perfectly, but we invite you to maybe swap the model or change the hyperparameters in order to make it work better. Once that you're satisfied with that training, you can evaluate it in one of our evaluation scenarios and submit your entry to the leaderboard. The expectation would be that towards the end of this activity, we'll have a few baselines, and probably there will be some prizes, although I cannot promise just now, to whoever reaches the highest place in the leaderboard. If you want to learn more about this, you can go to the blogs in flower.ai website and read this blog that Yang Gao, who is the leader of this initiative, put together. In there is also a video tutorial that shows you how to start to participate in the FlowerTune LLM leaderboard. I forgot to add it to the slide here, but there is also a dedicated Slack channel about it. And related to this, tomorrow, so we launched this a couple of weeks ago, and tomorrow there is going to be an Ask Me Anything session where Jan and me are going to be live taking any questions you might have, whether they are super basic questions like where do I start, or maybe more advanced questions like, oh, I tried this, but my model is not converging. We are happy to help you with those questions. So feel free to join us tomorrow. Another piece of news from what we accomplished in the month of October, which was incredibly productive, was the release of Flower datasets 0.4 and Flower 1.12. We are particularly excited about the new two partitioners in Flower datasets. One of them which allows you to group entries in a dataset by user ID. This is interesting, for example, if you have a naturally partitioned dataset and you want to create groups out of this dataset. For example, if you have a speech dataset and you have different entries, one entry per user, you want to create a scenario where there are different users in that different users that are, for example, in a household, and you want to represent each household as a federated learning client. You can do that and many more with one of the new partitioners. There is expanded dataset support. This means implementing some tests for extra datasets. So now they are guaranteed support for them in Flower datasets. And then we also expanded documentation considerably. As for Flower 1.12, there are quite a few headline features. I think the main one was the introduction of log streaming. This is particularly relevant if you are running Flower in deployment, because as you probably know, typically the server app will run where the superlink or the super exec is, and fetching the logs from wherever you submit the run. You can make it work on your own with your own methods, but now with the log streaming, there is a built-in way of doing that, which makes everything so much more convenient. The Flower new templates, which are Flower new, if you remember, this is a command that allows you to start from a Flower project with just 3 lines of code, and you get a skeleton of a project using the machine learning framework of your choice that just works and makes it very easy for you, for example, to prototype things by replacing the model or the dataset with something that is more relevant to your use case. So we made some big improvements there. We got 2 amazing new baselines from people in the community. This is the FedRep baseline and the FedDebug baseline. If you remember, FedDebug was one of the talks in a Flower Monthly, I think 2 months ago or 3 months ago. It got merged very recently, so go check it out. And also there is quite a significant amount of work put towards the Docker support. So now running a Flower in deployment with a fully Dockerized setup, it is much more enhanced as well. And the documentation also makes it much easier for those that know a little bit less about Docker, to start in this dimension. Now it's much easier. And there are many updates, like updates to examples and much more. So I invite you to take a look at this blog post if you want to get all the details. And here in the corner, you will see that I'm saying that Flower 1.13 is coming soon, and it is true. Likely by the end of next week will be out. And the bigger focus is going to be the deployment engine. So if you're running Flower in a deployment, whether it is with real big clusters spread around the world, or maybe you're running FL on small devices like Raspberry Pis, this will be highly relevant for you. So stay tuned for that. Final piece of news, I think, is the introduction of 2 really exciting new pages in our website. They are in the industries section, and you can find them if you scroll down on the main website on Flower. You can find the links there. They present some real use cases of federated learning for automotive and finance. And I think it provides also a good motivation and background on why FL and federation analytics, for example, makes a lot of sense in these type of scenarios. So with this out of the way, remember, you are welcome to submit any questions at any point. Also, the panelists, you can interrupt me, ask me questions if you want. But if there are no any, we can jump straight into our first talk, which is going to be, where is the testbed for my federated learning research? It was a work put together by Amandio and Janes, both, I believe, when they were in KAUST. Yeah, so the floor is yours.
So, yes, hello everyone. I'm Amandio, research software engineer at KAUST. And I want to start by saying thank you to the Flower team for giving us the opportunity to talk about our work once again. We talked about an initial version of this current work. We had the chance to talk about this initial version of this current work in the Flower Summit of this year as a poster. And now we're here talking about it in the Flower Monthly. So we're very thankful to get the chance to share this with the Flower team, Flower community. Okay. So in this work, like Javier said, we're going to talk about our work, which we provocatively titled, Where is the Testbed for My Federated Learning Research? This is a collaboration between KAUST and University of Ljubljana with contributions from Janis, Boris, who is in the audience, Professor Velko, Professor Marco, and myself. Okay, getting right into it. The main challenges in evaluating federated learning algorithms are, one, the limited access to a diverse range of real devices, and two, the complexity of conducting experiments across these devices, all while measuring various performance metrics, such as inference accuracy, energy consumption, and time to convergence. However, due to these challenges, most FL evaluation results refrain from using the real devices where they aim to deploy their FL solutions, and instead they resort to running simulations. But if we never evaluate the algorithms on real devices, we're left wondering how they perform in real devices. What is the algorithm running time? What is the computational memory energy demand? And how do these change under real-world constraints, such as data, network, and device heterogeneity? To answer these questions, we decided to create a project with the goal of making FL evaluation over edge devices more accessible. And from this project came Collext, the collaborative learning experimentation testbed. So Collext offers a federation of 48 edge devices split between single-board computers and smartphones, allowing their users to reveal hidden hardware metrics, such as energy consumption and any potential hardware bottlenecks in the algorithms. But we didn't just want to offer the testbed. We also wanted to make it extremely easy to run FL research code on these devices. So we created a system that automatically gathers hardware metrics, helps you visualize them, and also takes care of orchestrating the experiments across the different devices. And all of this can be achieved by just adding 2 decorators to your Flower code. Okay, now we're going to take a look at the device composition in Collext. So we have 48 total devices, but we wanted not just to have a large pool, a large number of devices, we also wanted to have a diverse range of devices. And they needed to cover different architectures, performance capabilities, and hopefully also different vendors. For single-board computers, we have Orange Pi, which is that has an ARM architecture. We have Latte Panda, that is an x86 machine. We have 3 generations of NVIDIA Jetsons. So these are powerful single-board ARM devices that have CUDA capable GPUs. And then on the smartphone side, we're currently only using Android devices, and we have 6 total different brands, including Xiaomi and Samsung, Google Pixel. And these smartphones, we again wanted to have a nice variety So to pick low, mid, and high tier devices, we actually used a website called AI Benchmark that has rankings as to how different smartphones behave in different in benchmarks of AI inference. So based on these benchmarks, we picked a selection of devices so that we have low, high, and mid-tier devices. And in addition to these devices, we have a dedicated server that will act as a federated learning server. And this server also includes a GPU, which sometimes is required for certain types of federated learning, such as split learning. And we have a dedicated networking connecting all of the different single board computers and smartphones. And finally, we have a high frequency power meter, which we have used to measure the power consumption of smartphones directly. So just as a note, building and configuring the testbed required a lot of effort. So we actually documented our experiment experience, and so that we could assist further other research groups interested in creating their own testbed. And we'll give details. For more details, we'll share a link at the end of the presentation, but we hope this can be beneficial to other people. Okay, so now we saw the devices. Now we're going to walk through how you can actually interact with Collext as a user. Okay, so here's a quick overview of the interaction process. The green part shows the input that the user needs to provide, and the yellow part represents everything that is automated after that. So Collext will take care of this. Okay, so the first part, the first input that Collext needs is the FL code that you wish to run. And currently, Collext works with code written with the Flower framework. So we're targeting Flower specifically for now, but we try to make it general for other frameworks if we can. But to make it usable, we can just use default Flower code. We need to also add two decorators to it, one to the Flower client and another one to the strategy. But those are the only modifications you would need to your code. And then the other thing you need is to specify a configuration file that Collext, to tell Collext what you want to run and which devices you want to use. So you would specify the entry points for the client and the server, and also the devices that you want to use, the device type and the number of devices. And note also here that Collext, as part of the environment, Collext offers or exposes environment variables that you can use in the arguments, for example, the server address. So this is something that Collext will give you. And also, for example, if you need to know the number of clients, this is also something we provide as an environment variable that you can use in the configuration script for the entry point. Okay, so with those finished, the working directory can look very simple, just like this. We have the client code and the server code, which includes the strategy, a requirements txt file that lists all the dependencies, and the configuration file we just saw, where we specify the entry points and the devices we're going to use for the experiment. Okay, so that's really it from the user side. After that, Collext takes over. And at this point, all we need to do is from the directory of the code, invoke a Collext command, which is called Collext launch job, to launch the experiment as a job. And this experiment does a few things. One, it packages your code in the Docker container for the SPC side, for example. And then it deploys it to the node that you requested as part of the configuration file of Collext. And now the code is will start running on the devices. And because you decorated your Flower code with the Collext decorators, that decoration actually instruments the code so that we collect a bunch of different metrics. So we record hardware metrics and round statistics automatically just from the two decorators. Yeah, so we packaged the code, we deployed it, we're recording metrics, and printed while the experiment is running. You also get the job ID and the dashboard link that you can use, that you can access to monitor your experiment in real time. So here's what the dashboard looks like. In this image, you see two metrics that we're collecting. So one, power consumption, and another, GPU utilization. And you see we have some filters because with many rounds and many devices, interpreting the metrics can be quite challenging. So you can filter by specific rounds and specific lines that are being used in the experiment. And we also have this really neat feature where you can highlight the portions of the experiment that correspond to the different stages of NFL round. So fit here is shown in blue, and in red you see the eval stage of the round. So this really help you see the spikes in power consumption as the devices start doing something. Yeah, and we hope that this dashboard, we found that this dashboard can be very useful to see and interpret the different metrics that we're collecting as part of Collext. Okay, but you don't just get access to the dashboard, you also get access to the raw metrics that you can use to do further processing if you want. So here we're seeing the CSV file of the hardware metrics that you get access to once you finish running the job. And to also provide quick insights, Collext automatically generates plots from these CSV files. So in this example, we're looking at one of the plots where we can see, so all of these lines correspond to one device, and we're seeing the training time for these devices, energy during the training time, and energy for the entire round. So even outside of the time that this specific device has been training, so considering the slowest device. And we see this split between the fit stage and the evaluation stage. Okay, so we saw roughly what Collext is, how you can interact with it. Now I'd like to discuss a few use cases that we see might be interesting for FL researchers to use Collext with. We're going to talk about a total of 4. The first one is about comparing, revealing the trade-off really between accuracy and the resource usage required to achieve a certain accuracy. So in FL research, the final model accuracy is the most commonly reported metric, but the resources that were required to achieve the metric are rarely ever considered. So if we, for example, consider the energy required for the algorithm to reach its maximum accuracy, we might find that for a very small delta for a very small increase in validation accuracy, you might need to expend a lot of energy, which might raise some bells in your mind, and you start wondering if this small benefit of accuracy is actually worth all of this energy that you're expending to achieve it, especially if you're working on devices where energy is very limited or a very precious resource. So to play with this idea, we actually tested 3 federated learning algorithms on Collext with different model configurations and different value for different number of percentage of client participation per round. And our results do show that some algorithms consume significantly more energy for a very small accuracy improvement. So as an example, we can look at the blue square at the top right and a very high pink triangle here. So these 2 settings, doesn't really matter what they are, but we see a benefit of about 2 to 3% accuracy increase. But if we consider the price that we're paying in terms of energy, we see that we're asking for 2 or 3% accuracy increase for 3 times more energy, which might not be worth it under certain circumstances. Yes, another valuable exploration or another possible use case for this is if we're evaluating these different algorithms in terms of the resources that they need not to reach their maximum validation accuracy, but to reach a target accuracy. And here we also see potentially expected but interesting trade-offs where if we look at these yellow shapes here, it's where we use the least amount of client participation per round. And this results in a higher time to accuracy, but because we're using few clients, actually the energy required is the lowest of the configurations. But this can shift, and we might find that some configurations using all the clients can be very fast and use a lot of energy, but maybe the algorithm and the devices are willing to pay for this. Bottom line, by looking at these values, we can get a better understanding as to how these different algorithms balance out the speed and energy efficiency, which can be interesting. Okay, so that was the first one. Second one, we will see how we can reveal efficiencies of on-device training. Okay, so for this, we are actually going to be using the Moon baseline from Flower baselines and examine the training time and energy consumption per batch across 4 different models of NVIDIA Jetson devices. So these are single board computers with a GPU. And the model of the devices is here in the bottom right, with the oldest device at the bottom, the Nano, and the most recent or the most powerful device at the top. And the results show that, as expected, the fastest device is indeed, or the most powerful device is indeed the fastest in the setup. However, we actually see that it's not significantly faster than the second fastest, the Ori Nano. However, it's paying a disproportionate amount of energy to reach this small increase in training or decrease in training time. And so with this, we start wondering, how can we actually quantify whether the decrease in training time justifies this additional energy cost? And this led us to consider a common metric in digital electronics called energy delay product. And this metric multiplies the time taken to complete a task with the energy required for the task to be completed. Thus, this means that a lower EDP value indicates that a solution would be both fast and also energy efficient. And if we now use this as the metric to compare the different boards, the single boards, different boards, we see that based on this metric, the Ori Nano is the most efficient device. In other words, if we considered our subset of devices, these 4 here, if we only use the Ori Nano for this algorithm, we would minimize the time taken to train a batch for the given energy budget and vice versa. And then we started wondering how this would change if we use another algorithm. So we used FedProx, also from the Flower baselines. And we saw that the general EDP rankings hold between the different devices, but surprisingly, the bottom 2 devices actually change in terms of efficiency. So it's interesting to see that the device efficiency can actually change across algorithms. And a final use of EDP can be to use it as a tool to evaluate modifications to algorithms. So you might be wondering about 2 different implementation details for your algorithm, and you can use this metric as a metric to help you determine if those adjustments that you're considering actually lead to efficiency gains. Okay. So third point, I'm going to see we can also use collects to help us identify implementation issues. As we were comparing Moon and FedProx, so from the Flower baselines, and we were looking at the round time between these 2 algorithms, we saw something that surprised us, which is that despite their similarity, we anticipated that Moon's additional forward passes would actually increase its time cost, because unlike FedProx, which only does a forward pass on this training, Moon actually completes 3 forward passes per round. However, when we look at the round times, these normalized times here, we don't see that it seems very narrow. And so this led us to think that potentially the issue is that we're not using a big enough model for these experiments. And the answer was yes, actually. But then the problem became, or the difference became too apparent, because if these are the only differences, the forward pass between the 2 approaches, now the difference is too large. So we looked at the code, and we actually saw that just one single line of code where we think we saw it contained the necessary GPU to CPU memory copies were enough to cause this slowdown. And once we tweaked it, we actually saw that we finally saw the performance of the Moon baseline more in line with what we expected. Okay, for the last one, we're going to talk about an example of smartphones with smartphone devices. And we did a lot of extensive experiments with smartphones that identified two main causes for mobile stragglers, and which are, as expected, both due to hardware heterogeneity. First, there's compute speed differences, which can be very noticeable during model training, not as much during inference. And in the plot here, we see a CPU trace of NFL round filtered to 3 smartphones with similar CPUs. You can see when the round starts with this jump in CPU utilization, and when it drops, it's when the round or this device finished pushing its training results back to the server. And you see that even though these smartphones have similar CPUs, the blue line here is significantly slower than the other smartphones. It takes longer to go down after it's went up. And this is surprising because the CPUs are similar, but if we actually look at the power consumption, this helps us understand what the issue is. Because while the other two smartphones show an increase in power consumption during training, and when they start training, the decrease when they stop, this device actually stays low for the entire duration, which means that the CPU is actually underclocked. So even though you know the CPU specifications, if you just use it without actually testing the device on a real setting, you don't know if there's actually some settings that might affect the performance of the device. Yeah, another use case, very quickly, is the data reception and transmission, which can vary across devices and can be very different. So here we have two devices transmitting the same model, and we see that the amount of uploaded bytes, so this is the process of transmitting one model to the server, can vary a lot between the devices, even though they claim to have similar specifications. Okay, I'm almost done. I just wanted to mention that we wanted to deploy a lot of Flower code, different Flower code, to make sure that our system was working. And so we're very happy to use the Flower baselines as a source for this repository of third-party Flower code, so not our own code to test on the testbed. We were happy to see that most of the Flower baselines that we deployed were actually ready to go. We found some didn't work. One, for example, was because there was some decoupling that was needed between the server and the client that was shared in a simulation environment, and that was okay. But as we decoupled them in the real experiment, that was an issue. And there was another one where there was unsupported serialization, where the client was trying to send something to the server that the server couldn't support. And so this seems to work in a simulation, but didn't work as we tried to use it on the devices. Okay, the limitations. So we have, unfortunately, our Android deployment requires some effort. You can't directly use your Python code. It supports Kotlin, and we don't support also any machine learning platform because there's no support for it in general. But we have experiments working with TensorFlow Lite, and we provide a code template that you can use to get you started and hopefully alleviate some of the issues. We also are struggling to combine experiments between Android and SPCs. For now, we have to pick one subset between these two. This issue is because of the model incompatibility as you try to combine the two different machine learning frameworks. And we don't have network emulation, but we want to support it relatively soon. Okay, I'm sorry, I went a little over time, but we are finished. I want to mention just that Collect is available to interested researchers, and we hope you find it useful. I want to mention that we wrote a paper based on this work and was accepted at the ACM IEEE Symposium on Edge Computing this year. And you have this QR code here at the bottom that you can scan to get additional details, and also a link to the paper. And yes, that's it. Thank you. We'll be taking questions.
Thank you for the super interesting talk. Now, as you were presenting this, I started to remember some of the things we discussed in the Flower Summit. Or I think we discussed, I'm not 100% sure, but yeah, I took some notes about some questions I have. So, because we are, not me, but in Cambridge University group, we are trying to do something like building a cluster of devices a bit, but it's not nearly as polished as this. So this is amazing. So my first question is, in your YAML, you specify what devices are going to be exposed to the experiment, for example, right? You have a list of devices.
Yes.
Does this mean, is this exposition of devices happening at the strategy level? Like the strategy does when it does a sampling of clients, it filters them out based on some metadata, or is done much earlier? Like I'm thinking from the perspective of a standard job scheduler to other platforms like Slurm.
Yeah.
Like, oh, in this job you only have 2 Raspberry Pis, 2 Jets and Nanos, and there's no way you're going to see the rest.
Yes, the second approach. So we control the devices that the experiment sees by controlling which devices we use for the deployment.
Okay.
So we only so if you ask for 2 Jetson AGX Orins, we only deploy on the 2 AGX Orins.
Okay. So this, for example, enables 2 experiments happening at the same time, as long as there is no overlap between clients, for example.
Yes. Yeah, theoretically, yes. We currently are working, we're still debating if we want to implement this as a solution, because given our current number of devices, it might be too small if we want to run interesting experiments, because even though we aim to have a large number of devices, we still only have 48 total devices. So assuming 2 users could share these 48 devices, I think it would be great if we could share.
I think 48 is not a small number, but I agree that some experiments do need a big number of clients. Okay, another question I wrote is the metrics that are captured at the strategy. Well, I don't know, are there metrics? So clearly there are some metrics being reported to your dashboard or being generated from the clients, but I don't know if from the strategy itself also. But my question is more, are clients streaming their own metrics, or are they being routed through the strategy, and the strategy is, for example, the only place where it's written into a CSV or is logged in your metrics S3 or whatever.
Yes, we're currently not going through the strategy, so we have a separate channel to send the metrics.
Okay. Interesting. I have one question about some of the results you were showing in slide 16. I think you were showing, like, I think a very interesting observation, like even if you train for 5 times longer, then the extra accuracy you get is very small.
Yes.
Oh, wait, no, it was a different slide.
This one?
This one, yeah. Could you give some insights on, if you remember, like how did you partition the data, for example? Because I guess it will be very different if it's like how fast everything, the accuracy curve plateaus. Maybe it varies between an easy FLS setup or a difficult one.
Yes. I think so. I wasn't the main person working on the experiments. It was actually Boris, who I think is not in this part, but in the participants. But we do have this information in the paper. I'm seeing if I can find it in my backup slides.
I think don't worry too much. I will take a look, but yeah. No, I think it's an interesting observation.
But it definitely to answer or part of it, the question, it definitely changes as the results that you plot here definitely change depending on the data that you're using and how you're partitioning the data, for sure.
Mhm. Okay. I think these are the main questions I had. Also, well, I like the table you showed at the end of the challenges you identified with different baselines you tested on. I think that was, I took a screenshot. I think that's useful for me to know. Well, but if you, now that you have identified some of the problems, like the moon problem you mentioned about the unnecessary copy, if you want to do a small contribution, that would be one example.
Yeah, maybe that I'll start there. Yeah.
Any more questions? I'm checking if in Slack there are questions, or anyone from the audience has a question, you can write it in the chat and I will read it. But otherwise, maybe we can go for the next talk since we are a bit over time. Okay, well, thank you very much, Amandio and Janis, for this super interesting work.
Thank you. My pleasure.
I'll be sure to check the repo. Thank you.
Thank you.
Thank you.
Okay, I'm going to share, let me introduce our next speaker. So the next speaker is Tsitsi C, if I'm pronouncing correctly. Sorry if I'm not. He's the co-founder and also works as an engineer in Kung Fu.ai. And he's going to be talking to us today about FLWR serverless, a serverless and asynchronous federated learning recipe for medical imaging. So I'm really looking forward to this talk, and the floor is yours.
Yeah, happy to share our journey in applying Flower and adapting it to a large scale use case in medical images. And this is a joint work with Senji, Reese, and Krishi. Yeah, so without further ado, let me first do a quick intro. So my name is Zidi Sai. I'm a co-founder and engineer at Kung.ai. And my background is mainly in computer vision and generative AI. And Kung.ai, our firm, is a management consulting and engineering firm focused solely on AI. We're based in Austin, Texas, in the United States. And what we do is that we empower CEOs and senior executives in different companies to leverage AI to stay competitive in this rapidly evolving world. And we provide both practical AI strategy as well as engineering solutions. And we're lucky to work with a client recently in the medical images field. And the main work around federated learning happened back in 2023. So this company is a really great company. They're doing groundbreaking work in breast cancer prediction using mammogram images, very high resolution mammogram images from screening. So the AI model there is used to predict the cancer risk up to 5 years in advance. And this really enables life-saving early detection. So really, really good company. And when we work on training AI models to use mammogram images to predict risk, there are several technical challenges. First of all, this is pretty common in the healthcare industry, is that there are multiple institutions that we get the data from, and these are very sensitive healthcare data, so there's very strict compliance requirements in terms of the data shouldn't leave their individual institutions, which makes it a perfect use case for federated learning. The data sets are pretty massive, millions of images, and because the tiny details in the images are pretty important for cancer risk assessment, so we need a high resolution of image, which increases the training cost. And last but not least, a lot of experimentation is needed to arrive at a good model. So we need good data, we need a lot of experimentation, we need to find a good recipe that gives us a high accuracy of the model. And luckily, we found Flower. We did a research to find what tools are available for federated learning, and Flower is our choice. And we really like Flower as it provides a flexible way for federated learning. The high-level design is very, very clear and easy to understand. So in this simplified diagram, basically, you would have. Oh, can you see my mouse moving or?
You can see, yes.
Okay, great. Yeah, so it's pretty easy to use. Where within each institution, you can start the Flower client, which uses the data in there to train a model. So we have Flower client 1 and Flower client 2. And then separately, you have a server here, which stores the model weights and aggregates the model weights. So the client, after a period of training, would upload the model weights to the server. The server waits for the all the model weights from the clients, and then it does the aggregation using a federated strategy, and then send back the aggregated weights to the clients. So this way, the data doesn't have to leave that institution. Only the model weights gets uploaded to the server. So you preserve security and privacy, and then you also have the benefit of the model learning from multiple institutions of data. And in our initial deployment, and we use AWS as our infrastructure. So we collaborated with the AWS team to set up the infrastructure where the server is deployed using ECS, Elastic Container Service, while the training jobs are managed by SageMaker. And the data are stored in S3, and we also have a MLflow server to track models performances. Yeah, and these are under different AWS accounts. So, for example, Institution 1 uses their AWS account, hosts their data, and same for Institution 2. So we were able to start large federated training runs, which is great, thanks to Flower. But still, we saw some operational challenges. And there are several kind of the pain points that I will talk about. One is that, and again, the caveat is that we did this work in 2023, and probably a lot of improvements already happened to Flower. So this is in 2023. So one type of my pain points is related to server management. So we found that we needed to manage separate servers for each experiment. So we do hundreds of experiments. Each experiment can run for days or even 1 to 2 weeks. Pretty long training jobs because of the data scale. And managing separate servers for a large number of experiments is a pain point. So that makes it hard to scale to hundreds of experiments because of the overhead. And then another thing is the synchronization issues, in that the different institutions, they have different amount of data, they have different compute quota. Although they're all under AWS, they may have different GPU instances, for example. The data schema is not the same. The model itself, especially the classification heads, because we do multi-pass learning, the model architecture are not completely the same. So all of these reasons cause uneven training throughput. So some clients train quicker, some clients train slower. And in synchronous training in the federated server, it always waits for the slowest worker to finish the job, and that's a overhead. And because we do a lot of experiments, we iterate a lot on our code base. So oftentimes there may be bug here and there, and the training jobs may fail due to various different reasons, out of memory or any other issues. The server sometimes may have some networking issues. So different instabilities happening in anywhere. So that caused the whole training job to fail, which is a huge waste of resource. So although we were able to run some federated training jobs, because of the multiple points of failures, we ended up not having a lot of successful end-to-end training rounds that can last 1 to 2 weeks on all the data. So we thought that the main issue is fault tolerance. So when something, when some crash happen or some bug happen in any part of the whole system, how do you make sure that it doesn't bring down everything? So 2 ingredients that may help. One is delegation. So instead of centralized control by the server, how about, hey, let's have the federated clients help themselves. So aggregation happens on the server by default. What if but the aggregation itself is not very resource intensive compared to the training itself. So the clients, which the client machines typically can handle the aggregation. So how about just let the client handle the aggregation? And then what that means is that instead of needing a server that's actually listening and aggregating and sending the weights back, you really only need a centralized storage or a common shared folder. So that, different workers, different clients, they do their job, they upload their model weights to the folder and then see what others have put in it. And then just do the aggregations themselves and then just keep on training. So that's one idea, is the delegation to the clients. The second idea is to reduce weighting by asynchronous federation. This is not new. There are a lot of asynchronous federated learning algorithms. So this the faster training nodes doesn't have to wait for the slower ones. All right. So the implementation is also kind of straightforward, thanks to the great design of Flower interface. All we need to do is to move the aggregation from the server to the clients. Now each client will do their own aggregation on their own, and we no longer really need an active server. We just need a shared folder. Yeah, so conceptually, it's pretty straightforward. And how we implement it is that we, in our particular implementation, we have a class called async federated node, which kind of does this, does the training similar to the Flower client. We renamed it to node to simplify that. There's no longer a client server relationship, but we have compute nodes. And this class has one main method called update parameters. So what it does is that it takes the local parameters, which is really the model weights of itself. And then it'll look in the shared folder and see if anyone else uploaded any new weights that it hasn't seen before. And then gather those. So the weights of itself and other nodes' weights, and then simply pass it through to Flower's federated aggregation matrix for a federated strategy. Yeah. And with a great interface of Flower strategy here, where you have the aggregate fits, as long as you tell it, server round, the results, which has the model weights from different training nodes, and then that method will do the aggregation. So yeah, that is our kind of pass-through implementation, which is really a wrapper around Flower core. And for synchronous training, it's also kind of similar, except that we now add some weights. We use it in Keras mainly because for our clients, we use TensorFlow Keras, and we added a callback, which is really a simple wrapper around the federated node. And all it does is every epoch, it will convert the Keras model to NumPy arrays called a async federated node. So it's pretty easy to integrate it into Keras training pipeline. For PyTorch, it's also similar. We also did Hugging Face transformers integration. So with that, we were able to run hundreds of large-scale federated training runs that finally finished successfully, and we were able to have a highly accurate model that's deployed. And this is due to the key benefits. For example, there's no more server management, better fault tolerance, and nodes can even come and go. You don't have to specify the topology beforehand, because with async credit, you can really have a flexible number of nodes that come and go. We did some experiments just to study the effect of async versus synchronous federated learning. What we learned is that async gave us roughly the same kind of accuracy compared to sync. And I want to add a caveat here is that we didn't highly optimize training pipelines here, and we didn't wait for it to converge. For example, for CIFAR 10, typically an optimized training pipeline you should get roughly 94%. And when we get 80, with this unmodified Keras training pipeline. It's pulled from the web. Some other learnings include that the skewness, which involves uneven distribution of training data in different institutions, where skew 0 meaning same distribution across different institutions, and 1 means it's a perfect partition of label. So for example, for CIFAR 10, dogs are always on one institute and cats are always in other institutes. So that definitely affects accuracy. We have more number of nodes. The accuracy typically drops in our findings using the federated average. And we have similar conclusion for ALP tasks, the language model. And I also saw this exciting news in the Flower team and think that this is a really exciting direction. And wouldn't it be great for smart people in the Flower community to train your own LLM using Flower? And I think that one endpoint of large-scale LLM training is fault tolerance, because the GPUs they tend to crash when you have a lot of GPUs running simultaneously. So adding fault tolerance would be great, and hopefully by incorporating some ideas of serverless and async learning, that will increase the fault tolerance. And lastly, just wanted to share the resources here. We have our GitHub repo that holds our adaptation of Flower. And we also have a technical report that summarizes our findings in a small scale experiments. And with that, I would like to thank you. So thank you so much for hearing me sharing our learning journey. And if you have any questions, feel free to submit a GitHub issue or let me know. Yeah, thank you so much.
Thank you very much. I think this was a very interesting talk. I like how you presented your work, like starting from what was experience using Flower as is, and then how to make it work for your particular use case where you were running like maybe hundreds of experiments. So that was really nice way of presenting it. I have some questions. The first one, I think the first one is more like applicable to many FL projects, which is, you mentioned at the beginning that when you interact with some, let's say, different organizations, each of them might have, of course, potentially different resources and things like that, but also they store their local data in different way. So you were using the term data schema. Have you, from your interactions with your customers and things, have you learned some good practices on how to navigate this heterogeneous data schema? Because in the end, what this might mean is that the training the training loop in each site might need to be slightly different, at least in terms of how to load the local dataset. So how do you navigate this?
Yeah, it's such a great question. And this actually happened for our for this particular project. So a little bit of context. So although the core machine learning problem is that you take several images as inputs and predicts cancer, no cancer 5 years down, but we found it is pretty helpful to do multi-task machine learning, meaning you predict not only the cancer risk, but also some auxiliary variables that's found in the data. And those auxiliary variables, for example, the breast density and some other metadata related to the screening and to the diagnosis, those are different in different institutions because the institutions span across the globe. In Europe, there's different data schema than in the United States, for example. So what we did there was that, and again, this is thanks to the great design of Flower interface, is that we would have a full model and a core model. So the full model is able to predict a flexible list of targets. So that made us able to adapt to different schemas in different institutions. But the core model, the backbone of the image, the image backbone stays the same and it's shared across the institutions. So when we use Flower to aggregate the weights, we only aggregate the weights of the core or the backbone of the model, while we keep the different heads, for example, different classification layer that's tuned to the different schemas. Those are local. Those are local to the different institutions. So yeah, that's how we implement it for this particular.
I think this makes total sense. But in the end, this also means that in order for you to evaluate how good your FL training is going, your only option is to do federated evaluation. Am I right? Given that you don't have a complete model in your server. Well, you don't have server anymore, but you know what I mean.
Yeah. So yeah, in terms of what's centralized, the model weights are definitely centralized, and also the metrics we also try to centralize in a MLflow server that's in the federated account, not in individual accounts. So we will collect metrics like the accuracy of the cancer risk prediction and there. So yeah, totally agree that you're doing the federated evaluation. Yeah. Okay. And
I have a couple of more questions, but if at any point anyone else, including you, Amandia and Janice, you have questions, feel free to jump in. So in the meantime, I will ask. Yeah, so I kind of I understood how you made the server kind of disappear and replace it with this concept of a shared folder. But I presume that this brings some implications, like, for example, the stages like client sampling, it doesn't exist anymore, or meaning that all clients participate all the time. And also, is this correct?
yeah, I think that's totally correct. Like, all the aggregation that used to happen on the server in our implementation will happen in each of the clients. So there may be some duplicated kind of aggregation happening now because each client now does its own aggregation. There's some overhead, but I think it's only worth the additional fault tolerance. There are additional kind of risks that we have thought about. For example, if different clients have different versions of the code, would that break things? So I think there are definitely things that we need to think more about to make sure that there is a clear guideline or clear kind of best practices when we do the more decentralized training like this. I think protocol matters, convention matters. We need to make sure that in the shared folder there's a clear naming, things like that. So yeah, if there's more time to continue working on this path, collaboratively, I think we need to talk more about the protocol of collaboration.
I think that was interesting, the concept of the shared folder. I have one follow-up question about this. How do you handle, for example, setups? So what will likely happen is that each client aggregates at a different point in time, right? So
Right.
it's highly likely that different clients start working with a aggregated model that is potentially not present in any other client. So do you, let me present it in a different way. If we have 10, let's say 10 hospitals or 10 research centers, one of them is going very, very fast because it has very few images.
Yeah.
And this will create a situation that its local model is pushed to the shared folder, so others can pull it, and it also pulls all the updates from that other clients push. How do you prevent from, making aggregations where no update has been pushed by other clients? Like, do you keep track of?
Brilliant. Yeah, let me make sure I understand the question. Is it that different institutions, they have different training speed, they have different data size, and some already trained a long time and some are new, they just started training and started pushing their weights. Would the weights corrupt the federated status? Yeah, I think that's a great question. I think there's definitely a lot of room for improvement in terms of stale awareness. Like, can the I think it depends on the quality of asynchronous federated strategies to be able to recognize, oh, this is a very new model that's only trained on 100 data points. And this model weight is trained on 2 minutes already for 7 days. Then I should take those into account when doing aggregation and be able to adaptively cut the model weights based on different staleness and other situations. So I think there's definitely a lot of room for good asynchronous strategies. And in my experiments, I only tried Fed average, Fed and Fed average averaging. That's the mean again. I tried several others, but surprisingly, I found that Fed average is still the overall the best performance. It's pretty hard to beat it, but I think that's because I haven't tried some of the newer ones since 2023. So very excited to learn more about other strategies.
Yeah, cool. Very interesting. I think, to comment on that, I think Fed average usually is a pretty good starting point, in my opinion. Like, if the data distribution over clients is very complex, then Fed average might start falling apart. But in many settings, I think is the right way to start because you remove the complexity from the aggregation side. So pretty cool. Okay, are there any other questions? I think final opportunity, Amandio and Janice, if you want to ask something. Okay, then if there are no questions, well, thank you very much once again for this super interesting work, and I'll keep this in mind. I remember you opened an issue not long ago proposing how to bring these serverless ideas into Flower. So definitely something we want to look into. And as I mentioned, we are planning some big changes in how the deployment engine works in Flower, and I think this will become highly relevant. So we can revisit this in the weeks to come, I think.
That is awesome. Thank you so much, Alex.
Okay, I'm going to share the slide just to close the Flower Monthly. So thank you everyone for your time and for putting the effort to put together the slides and freeing your calendars to tell us about your interesting research and projects. The Flower Monthly will be happening again in the next month. Usually, well, it's always on the first Wednesday of a month. That will be the 4th of December. So hopefully I will see you there as well. And this video, as I mentioned in the beginning, will be posted in our YouTube channel, and you will get a notification sometime next week, most likely. So thank you once again, and well, take care. feel free to reach out to the Slack to me or any of the other speakers if you have any other questions. Thank you.
Awesome. Have a great day or night.
Bye.
Thank you.